Hello? Okay, we can start now. So before going into, we can first see what is the previous class. I mean, this class Sir has taught. Okay, this today this class is all about the weldability of the material. So weldability is a capability of the material to be welded under the fabrication conditions imposed into the specific suitability, designed structure, and to perform the satisfactory in intended service. Okay, so it is the ability of the material to be welded under the fabrication conditions. It is like a if certain kind of materials are difficult to weld, even though we do welding, its properties are not same as the before welding conditions. Such kind of things we should consider while doing this kind of before choosing the any material for the any applications. Okay, so economically, what is the so in compressing, what we have to see is that metallurgical compatibility, mechanical soundness, and serviceability of the weld joint. Okay, first is the metallurgical compatibility. If they're doing the welding, the any precipitations are forming or any microstructure, any changes are occurring in the weld bead or so on, that we have to consider, or any segregation of the elements are taking place, those things we have to consider. And mechanical soundness, so the welded joint in generally we say the whatever we do the welding, if you do the any tensile testing, the base metal should fail before the weld joint. That is the general consideration for a good welding. Next is the serviceability of the weld joint. So in terms of corrosion or any other whatever the application we are using, it should be same as the base material. Okay. So what kind of effects of alloying elements in the valuability is that, so if we do any alloying, if we have a alloy material which has the certain kind of alloys, so what kind of effect on the weldability of the material is that, first is that it may increases the hardenability. So if certain elements are there which is the carbon equivalent to certain elements like chromium, nickel, and so on, so those may tend to uh, promote the formation of the martensitic phase. So that will result in the hardenability. So increasing hardenability from age hardened precipitation. So some particles may form due to the haze hardening, because we reaching it to certain temperature and we are holding it for a certain duration of the time. So aging may takes place and some precipitations may form. Okay, and providing grain refinement. So some elements can promote the grain refinement. Okay, and reduces segregation. So some segregation of the elements can be reduced, and controlling the ductility to brittle transformation temperature. Just like iron, if we go for the below 0 degrees and so on, it transfer from the ductile material to brittle material. So those things we have to control. And next, formation of the carbates. Suppose in case of stainless steel and so on, the chromium may tend to react with carbon from the matrix and forms the chromium carbide. So such kind of carbates also may form. Okay, these are all are the effects of the allying elements. Uh, okay, so how we do the weldability test? Okay, the purpose of the weldability test is to gather the information about behavior of the material during the welding for establishing the correct welding conditions. It provides the useful information about appropriate process selection, preheating treatment required, or energy input, and joint design. Okay. So purpose of the valuability test is that to see the material behavior during the welding conditions. Okay. So to get the information like what is the process, what is the welding process we have to use, whether we have to use the preheating or not, or energy inputs, what is the energy input we have to provide, and joint design, what kind of joint design we have to choose, such kind of things. Okay. Next, valuability test may be classified as a theoretical test, simulated test, and actual welding test. Okay. So theoretical welding test is that. So in this case, we will do the annealing up to, suppose in case of steels, we will do annealing up to 1150 degrees. Then we will cool it to calculate to replicate the what is the what is the during the welding condition, what kind of situation occurs, that we will replicate it. So once it is heat annealing done, we will do the bending of that weld bead to 10 to 20 degrees. So ideally, what is the metal property should be there, and what we have achieved, I mean, what is the bending during testing, what we have got it, those we can compare and we can figure out whether any properties have changed or so on. Based on that, we can calculate the what is the availability of the material. Okay. Next, simulator test. Simulator test, we will use a heating cooling in the small samples of a thermal cycle. Okay. And like the formation of the particular well. Okay. Next, so another actual welding test also there. Such a, in that one we can classify them into two ways. One is the fabrication welding weldability and service weldability test. In fabrication weldability test, we can do such kind of like a hard cracking testing, root to root cracking testing, hydrogen induced cracking testing. Such kind of test we can do. In case of service welding testing, we can do the impedance test, fatigue test, creep test, corrosion test, tensile hardness, okay, and bending test, impact test, such kind of test we can perform. So based on this, we can see some of the problems. Okay, weldability of the metal is best defined as a option A, easy of the melting the material, ability to form solid sound weld joint with desired properties. C, resistance to corrosion. D, ability to conduct heat. So option will be easier to the melt material. Every metal will be it is not if we have the low melting point, doesn't means it has a good valuability. That is not. Resistance to corrosion, no, that is not. It is material property. It doesn't, and ability to conduct heat, that is the no. So answer will be the option B. It is the ability to form yes sound weld joint with desired properties. Okay. Weldability refers to the ease of producing a defect-free weld that meets mechanical and service requirements. Okay. Next, which of the following is not a factor affecting the weldability? First is A, chemical composition. Yes, because whatever the elements are present in the our life, that will affect the weldability. Okay. Next, thermal conductivity. Yes, if the thermal conductivity is high, then we have to provide a more heat to the material, so that definitely affects the weldability. Next, surface roughness. No, because surface roughness doesn't affect any. Next, cooling rate. Yes, cooling rate also will affect, because faster cooling rate, it may forms the formation of the metastatic phase or highly deformed grains. If it is a slower cooling rate, it may forms the more equiatomic grains or like that. So answer will be the C. It is the surface roughness. Weldability depend on the metallurgical and thermal factors, not primarily on the surface finish. High carbon equivalent in the steel indicates. So if the high carbon equivalent present in the steel means it is the more hardenable of the material. More hardenable means more metastatic formation. Okay, that increases the crack susceptibility. So that means this is not a good one. So option A, better weldability. Option B, poor weldability. Option C, no effect on weldability. Option D, only affects the corrosion. So answer will be, it is the poor weldability, because high carbon equivalent means higher hardness, magnetic transformation, increasing the crack susceptibility. So next, which of the following improves the weldability of the steel? So which factor will improve the weldability in the steel? Option A, increasing the carbon content. Option B, increasing the sulfur content. Option C, reducing the carbon equivalent. Option D, increasing the cooling rate. Answer will be reducing the carbon equivalent. If you reducing the carbon equivalent, less formation of the metastatic phase, metastatic tendency, so less crack, less susceptibility to crack propagation. Okay, so option will be C, reducing the carbon equivalent. So lower carbon equivalent reduces the hardness, that reduces the crack tendency, that improves the weldability. Which property of the metal strongly affects the heat flow during the welding? Okay, what is it? A, electrical resistance. If electrical resistance increases, so heat generation will be more. That is not the factor here. Next, thermal conductivity. Yes. Next, option C, magnetic permeability. Option D, density. Correct answer will be thermal conductivity. So higher thermal conductivity results in fast heat dissipation and affects the weld pool size and cooling rate. Metal with the high hardenability generally shows excellent weldability, poor weldability, no change in weldability, no corrosion issues. So metal with the higher hardenability results in, as we seen, higher hardenability means formation of the hard brittle faces, that like martensite, and that will increases the crack tendency, susceptibility to crack formation. So that means it will result in the poor weldability. Okay. Next, which of the following is a metallurgical factor affecting the weldability? Option A, joint design. Option C, B, weld position. Option C, phase transformations. Option D, operational skills. So among them, which is the metallurgical factor? It will be the phase transformation. So phase transformation like austentic phase to martensitic phase strongly influences the microstructure and cracking. Which test is commonly used to evaluate the weldability of the steel? Which test we will use? Option A, tensile test. Option B, hardness test. Option C, carbon equivalent calculation. Option D, impact test. What is the answer? It is the carbon equivalent calculations. As you seen, if the carbon equivalent is increases, so carbon equivalent is increases, the it will result in the poor weldability. So we want to avoid that. So that's why we want to choose the material which has the low carbon equivalent, so that will have a good weldability. So answer will be C. So carbon equivalent calculation provides the quick estimation of the weldability and crack tendency in the steel. Okay. Next, which of the following metals generally has the best weldability? Option A, high carbon steel. Option B, cast iron. Option C, low carbon steel. Option D, tool steel. Answer will be high carbon, sorry, low carbon steels. Why? Because of the, as we seen, uh, carbon equivalent is less in case of low carbon steel. In case of high carbon steel, carbon is high, cast iron is also very high, and D is the tool steel. Tool steel also carbon equivalent elements also present, like other elements, vanadium, chromium, such kind of things. Those will affect increases its carbon equivalent. So answer will be C. It is the low carbon steel. So low carbon steel have a low hardenability, minimum cracking risk, and excellent weldability. Okay, next. Rapid cooling during the welding generally leads to increasing ductility, formation of the martensite, reduced hardness, the improved weldability. Answer will be, so rapid cooling will result in the generally formation of the martensite. So option will be D. So rapid cooling promotes the martensite transformation, increases the hardness and reduces the weldability. So here are the few key takeaways from the first lecture is that, so first factor, if the carbon content is increasing, the weldability reduces. If the carbon equivalent uh, uh, is increasing, the cracking risk will be increases. Weldability reduces and cracking risk will be increases. Higher thermal conductivity means it is a faster cooling. Higher hardenability results from the martensitic formation and phase transformation control microstructure. Okay. So next we will go to next section, next video, that is the weldability and the carbon steels. Okay. In valuability in the carbon steels, we can classify the carbon steel into four categories. One is the low carbon steel, mild steel, medium carbon steel, and high carbon steels. Okay. So in low carbon steels, we generally have the carbon content less than 0.15%. So that we can use for the sheets and strips and welding electrodes. And next is the mild steel, it is 0.15 to 0.3 percentage for the structural shape and plates, bars, most widely used material. And medium carbon steel, that is the 0.3 to 0.5 percentage. It is mostly used for the machine parts and tools. And high carbon steels, which is generally having the 0.5 to 1 percentage of the carbon content, which we generally use for the springs, dies, and rails. Okay. So weldability, coming to the weldability perspective, so low carbon steel and mild steel generally have the higher weldability because of it is low carbon equivalent content. So but medium carbon steel is the moderate, and high carbon steel is the poor weldability. Okay. So low carbon steels, steel with the low carbon content up to 0.13 percentage is a good weldable steel, but not best for the high speed welding. Why? Because high speed welding generally produces the porosity. Uh, if certain our component doesn't affected by the porosity presence doesn't affect it, then we can go for the higher speed also. Condition can be corrected by modifying the welding procedure, that is using the lower speed. So if the internal porosity is not strictly requirement, then standard high welding procedure may be used. So if the porosity is not a big problem, then we can go for this high speed also. So it is the generally low carbon steels have a good weldability. Okay, coming to mild steel also similar to the low carbon steels, we can have a excellent weldability with the mild steel also. So those are the used in maximum production speed and on assemblies and structures that required extensive welding. So where is the components required extensive welding, there we can use it because of its good weldability properties. And mild steel is the with 0.25 to 0.3 carbon content, and 1.4 manganese has the very good weldability. Through with increasing of the alloying elements on the higher side of the permeability limit, the filler welds are the particularly susceptible to underbreed cracking. Next, coming to the susceptibility to underbreed cracking. from hydrogen increases when carbon equivalent exceeds 0.4 percentage. Okay, so heavy sections may require the preheating. So why we have to provide the preheating, so that the cooling rate will be reduces. So if the cooling rate is reduces, the martensitic formation will be reduces. So that will also less preheating requires when low hydrogen presence is used. So and also if the cooling rate reduces, the any diffused hydrogen has the enough time to diffuse out. Okay, so steel with in the 0.35 to 0.3 carbon content should be welded with low hydrogen electrodes or lower H2 producing if ambient temperature is below 10 degrees centigrade. Okay. Similarly, medium carbon steel, if we go for it, is the moderate weldability. As carbon content is increased in the steel, welding procedures should be such as to avoid the formation of the large amount of the martensite in the HZ. So why it is a moderate is that main problem is that higher carbon content means higher carbon equivalent percentage, so that will hardenability is increases, that means martensitic formation is much more higher. So we have to provide a certain environment so that we can reduce the formation of the martensite. How we can reduce it? One is the providing the preheat treatment, and slower cooling rate, that will result in the slower cooling rate, and to reduce the stresses we can do the post weld heat treatment. Okay, in most of the applications medium carbon steel should be preheated prior to the welding to control the cooling rate in the weld metal and HZ. Okay, preheat treatment depends on the carbon equivalent value, that is ranging from 0.45 to 0.6 percentage, and may require the preheating temperature of 100 to 200 degrees temperatures depending on the welding process and work thickness. Okay, so next is the medium carbon steel's low hydrogen welding procedures is mandatory. In ways of multi-phase welding, low heat input is recommended for the first few layers and to limit the dilution. Okay, stress relieving post-weld treatment is recommended immediately after welding, especially in thick sections and high joint restraint or surface service conditions involving dynamic loading. Okay, next coming to the high carbon steels. So high carbon steels generally have the poor weldability, as we seen. If the carbon content is increasing, it is hardenability increases, and martensitic formation is more. So in that case, to prevent that, we have to, if the content is increasing, the preheat treatment requirement and its temperatures also increases. Okay, so if the in this case preheat treatment requirement is the 200 to 315. Suppose in case of medium carbon steel, it is the 100 to 150 to 200 degrees. Okay, so use of the low hydrogen produces minimize degree of the preheat requirement. So to reduce the pickup of the carbon by the weld metal, the welding procedure should be designed to keep the dilution minimum. Okay, so generally if the dilution is more, the more carbon element can be pick up from the uh, base material and HEZ into the weld material. So to minimize that, we have to use the uh, weld procedure should be designed so that weld dilution should be minimum. Okay, so high carbon steel should be welded in a annealed condition and then heat treated, and annealing is recommended prior to the repair and of the broken welding parts. Okay, post weld stress relief is recommended particularly for the welding joints of the thick section. As we said, so if in case of carbon content increases, we have to use the preheat treatment much higher. If the carbon content increases, the preheat treatment temperature also will be increases. Okay, so now we can come to some problems solving for this lecture. Okay, which type of the carbon steel has the has the best weldability? Okay, so as we seen, which is the lower carbon content that has the good weldability. So option A is the high carbon steel, option B is the medium carbon steel, option C is the low carbon steel, option D is the ultra high carbon steel. So option will be, so low carbon steel and mild steel both are the good weldability. So that is the C answer. So low carbon steel with less than 0.25 percentage of the carbon has the low hardenability, minimum martensitic formation, excellent weldability. Next, the main reason for the poor weldability in high carbon steel is option A low melting point, option B high ductility, option C high hardenability, option D low thermal conductivity. So answer will be, so it is the only factor which is the mostly affects the weldability is that its hardenability. So if the carbon content increases, it hardenability increases. So answer will be the C, high hardenability. So high carbon content results in higher hardenability. Formation of the hard martensitic phase in HZ leads to cracking. Next, which of the following phase is most undesirable in HZ of the carbon steels? Which phase is most undesirable? Option A ferrite phase, option B perlite phase, option C austenitic phase, option D martensitic phase. So answer will be, it is the martensitic phase, because martensitic phase generally has the higher hardness and brittleness. So because of its brittle nature, during the cooling process, the weld metal will become compact because of the volumetric contraction will take place. So during that time, because of its brittleness, it will break and crack will initiate. That crack results in the failure of the material. So martensitic is a hard and brittle, makes the weld prone to hydrogen cracking. Okay. Next, carbon equivalent is used to estimate what? Corrosion resistance, weldability of the steel, electrical conductivity, and thermal expansion. I think it is, we have, as we seen in previous questions, it is the weldability of the material, steels. Okay. So if the carbon equivalent is more, it is the poor weldability. If it is the carbon equivalent is less, it is the less good weldability and less tendency to crack formation. Which of the following increases the carbon equivalent? Decreasing the Mn content. So generally, if a Mn content is more, it is the less carbon equivalent. Okay, increasing the alloy element like chromium and molybdenum. So chromium and molybdenum generally increases the carbon content. Why is that? It high, these alloys are more prone to formation of the carbides and so on, like chromium carbide and so on. And C, reducing the carbon content. So if the carbon content reduces, carbon equivalent will reduces. Option D, increasing the grain size. Grain size is doesn't affect the carbon equivalent. So answer will be B, increasing the alloying elements. So carbon equivalent alloying elements like chromium and molybdenum. So alloying element increases the hardenability, raises the carbon equivalent value, and reduces the weldability. Next, which preventing measure is most effective for the welding medium and high carbon steel? Option A rapid cooling, option B preheating, option C increasing the welding speed, option D reducing the heat input. So answer will be preheating. Why? Rapid cooling means formation of the martensitic is much more higher. So increasing the carbon content means formation of the martensitic hardenability will be more. That means formation of the martensitic is much more higher. So to reduce this formation of the this formation of the martensitic phase, what we can do is that reducing the cooling rate. So how we can reduce the cooling rate? By providing the preheat treatment. So by providing the preheat treatment, we will slower the cooling and reduce the metastatic formation and allows the hydrogen to diffusion. Okay, and in comparison with the medium and high carbon steels, we have to provide the more preheating for the high carbon steel compared to the medium carbon steel. Okay, so next, which microstructure is expected in HEZ of the low carbon steel after welding? So which microstructure? A martensitic phase, B Bennettich phase, C ferrite plus perlite, D cementite. So in case of low carbon steel, there is a less hardenability will be there. That is also in HEZ. It will be the most probability is the option C ferrite plus perlite. So low carbon steel, low cooling is low enough to form the ductile and ferrite perlite phase, ensuring the good weldability. So hydrogen induced cracking in the carbon steels is most severe when option A low carbon plus slow cooling, option B high carbon plus rapid cooling, option C low carbon plus high ductility, option D high temperature plus low stresses. Answer will be B high carbon plus rapid cooling. This condition produces the metastatic phase and traps the hydrogen that results in the higher crack risk. So if high carbon content is there, high carbon equivalent is there, hardenability increases, martensitic formation increases. So that we want to avoid it. So best condition for the welding is that low carbon content and slower cooling rate. Okay. Next, which of the following welding practices reduces the HZ hardness? So which following welding practices? Option A increasing the cooling rate. Option B preheating and post heating. Option C increasing the carbon content. Option D using the dry electrodes. So answer will be B preheating and post heating. So preheating and post heating reduces the cooling rate and tempers the martensite and lowers the hardness. For steel with the carbon equivalent greater than 0.5 percentage, the weldability generally. So the 0.5 means it is much higher. So it will be option A excellent, option B good, option C moderate, option C poor. It will be the poor. High carbon content, carbon equivalent greater than 0.5 is the higher hardenability, high crack tendency, and poor weldability. So generally, what is the key points from this lecture is that low carbon means good weldability, and mild steel also good weldability. High carbon steel means martensitic formation and cracking. High carbon equivalent also poor weldability. Preheat treatment, by we use it preheat treatment to reduce the cracking, and rapid cooling increases the hardness. Okay. Next we will see for the alloy steels. Okay. High strength low alloy steels. So high strength low alloy steels are designed to provide better mechanical properties and sometimes better resistance to atmospheric corrosion than the conventional carbon steels. Okay. Weldability is similar to the mild steel. However, they often require preheat treatment, also control of the hydrogen in the welding process. Okay. Preheat treatment and enterprise temperatures are depending upon the carbon equivalent in the steel. The carbon equivalent is high, So we have to increase the pre-treatment and enterprise temperatures. When the welding of two different high strength low alloy steels together, higher of the two preheat treatments should be used. If there are two different the steels we are using, so which one having the high pre-treatment requirement is there, that preheat treatment we have to provide. So base metal is on each side of the joint should be heat treated to temperature over the distance equal to the section thickness or 80 mm, whichever is the larger. Okay. Commonly used welding process are SMW, shielded metal arc welding, GMAW, gas metal arc welding, FCAW, flux core arc welding, SAW, submerged arc welding, and low H2 process should be employed with all the processes. Okay, they can be welded using the ESW process, electro slag welding process, with no preheat treatment required because of high heat input characteristics. Okay, so one of the example of this high strength low alloy steels is that stainless steel. So at least to 11.5 percentage of the carbon is added to get the good corrosion resistance. So to the steel. So this film of the chromium oxide acts as a barrier to oxidation, rust or corrosion. Okay. So stainless steels can be broadly divided into following types like austenitic stainless steel, ferritic stainless steel, and martensitic stainless steel. Okay. So in austenitic stainless steel, carbon is generally 0.03 to 0.25 percentage, and manganese will be 2 to 10 percentage, chromium 16 to 26 percentage, and silicon 1 to 2 percentage, and nickel is the 3 to 3.5 to 22 percentage. Actually, this nickel factor is the it makes it this austenitic phase stabilizer. Okay. Next, ferritic steel, low carbon to chromium ratio. So here carbon will be 0.08 to 0.2 percentage, silicon will be 1 percentage, manganese will be 1 to 1.5, and chromium will be 11 to 27 percentage. And it is the good ductility properties and good magnetic properties, and it do not. Next, martensitic stainless steel. In this case, carbon to chromium ratio is high and magnetic in all conditions and can be cold cracked. So carbon content will be it is the carbon content 0.15 to 2 percentage, silicon 1 percentage, manganese will be 1 percentage, chromium 11.5 percentage to 18 percentage. Okay. So austenitic stainless steel, as compared to the carbon steel, austenitic stainless steel exhibit more electrical resistance, less melting point, lower thermal conductivity, and higher thermal expansion. So larger value of the expansion of the stainless steel increases the tendency of wrapping and distortion and higher chance of weld cracking under the restraint conditions. So allowance are made for the increase in the shrinkage in thick sections, and a skip welding process we can back step welding and use of the talc welds and position of the sections for the proper alignment are among the normal practices. Okay, so these are the some of the practices we can use, like skip welding, back step welding, to proper heat distribution, and use the thick torque welds and position section proper alignment along with the normal practices. Okay, when they are heated within the temperature range of 427 to 870 degrees centigrade, are cooled slowly through that range, carbon is precipitated from the solid solution at the grain boundaries, where it units intergranular with chromium to form the chromium rich carbates. Okay. The formation of those carbates effectively eliminates much of the chromium from adjacent areas, lowering the corrosion resistance and susceptibility towards the localized intergranular attack. Okay, so the carbon precipitation during the welding of the austenitic stainless steel can be minimized by reducing the time during the temperature range, um, and selection of the SS for the welding with lower carbon content and susceptibility addition of the carbide formation elements. So like titanium or like that, if we add it, those will form the carbon more prominently than the chromium, so that will retain. And appropriate heat treatment to avoid the intergranular corrosion, like adequate folding time, rapid cooling through 925 to 538 degrees centigrade, and cooling in air slash water depending on the thickness. Okay. Next. So next, coming to the ferritic and martensitic stainless steel. In this case, welding characteristics of the ferrite and martensitic stainless steels are different from the carbon steels, also from the austenitic stainless steel, because of the following factors. Ultimate tensile strength decreases rapidly with the temperature, and pro- pronounced grain growth is excess of 900 degrees centigrade. Okay, melting point below carbon steel, and expansion coefficient is same as the carbon steel. Okay, thermal conductivity is less than the half of the carbon steel. So welding of the ferritic stainless steel, in general, those steels are less valuable than the austenitic stainless steel when heated above 954 degrees centigrade during the welding, and growth of the ferritic grains is prominent. Okay, the larger grain size of the ferrite along the small amount of the martensite induces the brittleness and lack in the toughness and ductility at the room temperature in the weld. To minimize the grain growth, the preheating and interpass temperatures weld heat treatment are kept as low as possible. So grain coasting can be controlled by avoiding the slow cooling from the welding temperature. Intergranular precipitation if cooled too rapidly, hence heat treatment at 700 to 820 degrees is followed by cooling at the moderate rate is corrective treatment. Preheat treatment at 150 to 250 degrees is suggested, and post-well treatment temperatures are kept usually at 843 degrees centigrade to prevent the grain growth and austenitic formation beyond HEZ. Okay. So coming to the final one, welding of the martensitic stainless steel. During the welding, when martensitic stainless steel are heated, austenite is forms when subsequently rapid cooling generally large amount of the transformation stresses. So because of the martensitic has the larger volumetric compared to the austenitic phase, so a lot of transformation stresses will generate. The changes in the change chance of the cracking because of the low value of thermal conductivity, because it is the low thermal conductivity, especially in brittle microstructure formation by rapid cooling rate. For reducing the transformational stresses and increasing the toughness and ductility, preheating and post-weld heat treatment are suggested for the martensitic stainless steels. Okay, so let's see some problems. Compared to the carbon steels, alloy steels generally have better weldability, similar weldability, poor weldability, no relations. Option will be, it is the C. It is the poor weldability. Generally, low carbon steels have the higher good weldability. Alloy steels contains the chromium, molybdenum, uh, nickel, and vanadium. Those are increases the hardenability, so lead to martensitic formation and cracking. Which alloying elements significantly increases the hardenability and reduces the weldability? Option A, aluminum. Option B, chromium. Option C, copper. Option D, silicon. So answer will be chromium. As we seen here, chromium, molybdenum, vanadium, and nickel are the most carbide form, mostly increases the hardenability that will promote the martensitic formation. So we want that will reduce the weldability. Okay, so among the element is the chromium. Chromium increases the hardenability and promoting the martensitic transformation in HZ and higher the crack risk. The primary problem in welding low alloy steel is option A, corrosion. Option B, hydrogen induced cracking. Option C, grain refinement. Option D, oxidation. So answer will be option B. It is the hydrogen induced cracking. So due to the higher hardenability, alloy steels are prone to hydrogen cracking, especially in the heat affected zones. Next, which of the following steels requires mandatory preheat treatment before welding? Which is the higher carbon content and which is the higher hardenability? That is the there we have to use the preheat treatment. So such as option A, low carbon steel. Option B, mild steel. Option C, high strength low alloy steel. Option D, pure iron. So answer will be C. It is the high strength low alloy steel. High strength low alloy steel have the higher carbon content, so that requires preheat treatment to reduce the cooling rate and avoid the martensitic formation. Which of the microstructure is commonly formed in the HEZs of the alloy steel during the rapid cooling? Option A, ferrite. Option B, perlite. Option C, martensite. Option D, austenite. So answer will be faster cooling means it is the formation of the martensite. Which of the following improves the weldability of the alloy steels? Option A, increasing the cooling rate. Option B, preheating. Option C, increasing the alloy content. Option D, reducing the heat input. So answer will be preheating. Preheating improves the weldability by reducing the cooling rate. If the cooling rate reduces, the formation of the martensitic phase reduces. So it is good weldability. So preheating reduces the cooling rate, prevents the martensitic formation, allows the hydrogen to diffuse out. Next, which type of the cracking is most critical in LFC welding? So which is solidification cracking, hydrogen cracking, liquidation cracking, and crater cracking? Answer will be hydrogen cracking. because due to high strength and hard microstructure, hydrogen cracking is the most severe issue. Hydrogen cracking nothing but a cold cracking or delayed cracking. Okay. Most weld heat treatment, post weld heat treatment in alloy steel is mainly used to increase the hardness, reduce the residual stresses, increasing the cooling rate, formation of the martensite. Answer will be it is to reduce the residual stresses. Okay. Post weld heat treatment reduces the residual stresses, temper the martensite, and improves the toughness and reduces the cracking. Okay. Next, which alloy steel is particularly prone to reheat cracking? So which one is? It is the low carbon steel, austenitic stainless steel, chromium molybdenum steel, pure iron. Answer will be chromium molybdenum steel. Why? Because chromium and molybdenum are easily forms the carbides from the material. So if the carbides are formed, it will be prone to more uh, cracking. Chromium and molybdenum steels are high temperature applications prone to reheating and stress relief cracking. Increasing the alloying elements generally shifts the CCT curve. I think towards the right, it is the, I think it's a CCT curve, cooling curve, the C curve. If the C curve shift to right, the martensitic formation become less. Okay. So few of the crucial points is the alloying elements. Chromium, molybdenum, nickel increases the hardenability. So higher hardenability means martensitic formation, and if the hydrogen is present in the alloy, it is the results in the cold cracking. And preheat treatment, we can use it to reduce this cooling rate that will increase the weldability, and post weld heat treatment to provide to stress relieving and tempering the martensitic phase. Okay. Next, so coming to the welding of the cast iron. So cast iron is similar to the ferrous alloys that normally contains more has the 2% of the carbon content and the 1 to 3% of the silicon, as well as the some small element of the sulfur and phosphorus. There are the four major types of the cast irons. One is the gray cast iron. It is the weldable. White cast iron, it is not normally weldable, and malleable and nodular cast iron, weldable but require the post weld heat treatment. Okay, so gray cast iron is difficult to weld economically because major applications are repairing in casting in the foundry, repairing of the cast damage in the services, and join together separately cast sections. Okay. So malleable cast iron welding destroys the advantage of annealing treatment. Okay. And nodular cast iron changes the changes of the magnesium loss and minimizes heat input to avoid the graphite degradation. Okay. So welding characteristics of the gray cast iron is that in weld pool, the cooling rate determines the carbon going into the combined state or remaining in the free form. So cooling rate is reduced by preheating the pot to the temperature of 600 to 700 degrees centigrade, also cooling slowly. So post-weld heat treatment of the job minimizes the excessive cooling stresses, prevent the formation of the white cast iron. In grey cast iron, we have the graphitic flakes. So if we do the faster cooling, it will convert into the white cast iron. So other techniques in welding of the grey cast iron are uses of suitable non-ferrous electrodes of the low melting point than the grey cast iron. Use of the skip welding technique to minimize the heating of the gray iron component. So as we seen, so we can use the skipping methods welding technique. In arc welding, direct arm upon already deposited weld metal. In gas welding, flame should be directed on the welding rod. Okay, it is not to be direct on the welding bit. Next, filler metal should have some coefficient of thermal expansion as that of the grey cast iron. Okay, next, welding procedures for the grey cast iron are process applies for the welding of grey cast iron are SMEW shielded metal arc welding, gas metal arc welding, flux core arc welding, and oxy-fuel gas welding, brazing welding, and thermite welding. Preheating is done to decrease the cooling rate and preheat temperatures depending upon the factors like type of the cast iron being welded and mass of the casting and welding process employed and type of the filler metal used. Okay. All cast irons to be preheated during the oxy-fuel gas welding to reduce the heat input requirement. So local preheating should be gradual to avoid the cracking, especially in complex casts. Okay. So cast irons are welded with nickel and nickel alloys, mild steel, and the copper alloys covered electrodes. So root opening should be wide enough to permit good fusion into the root face and into the buckling plate if used. If butt welding with V edge preparation, 60 to 80 degree grooves angle, and for the thicker sections, U grooves with the 20 to 25 degree groove angle and 5 to 6.6 mm root radius. When repairing crack at the casting, a hole that 3.5 mm or larger diameter should be drilled at the end of each crack to prevent its further propagation. Okay, electrodes should be manipulated so that bead width is not greater than the 3 times that of the normal diameter of the electrode. For the filling large cavities, the side should be buttered with the weld metal first, then cavity gradually fill towards the center of the repaired area. Backstep welding sequence provides the better results for the larger castings to reduce strain caused by deposition of the long bead. Deposition of the weld metal should be in short length and allows each bead to cool down before laying next. Upset and pinning of the deposit weld metals lightly before it cools and and contract is another uh, alternative. Combination of the shot welding pin is the best practice. So buttering and studding are the methods of the getting sounded strong welds. So these are the some other methods we can provide this kind of drilling holes to the crack propagation we can provide, and suggested sequence like we can do the step sequence and back sequence welding so that the heat distribution will be uniform. So post weld treatment, the thermal stresses revealing treatment desirable for the fully restrained welds and weld intended for the use of uh, severe service conditions and subjected to closed machine tool tolerance. So done normally immediately after welding. If the casting is welded with the high preheat treatment and interface temperatures, it should be slowly cooled by the covering it with insulating and blanket or hot sand. So yeah, this is it. So we can see some other problems from this. The weldability of the cast iron generally excellent, good, poor, very high. Answer will be C. It is the poor. Cast iron has the high carbon content, brittle in nature, tend to form the hard phase, makes it welding difficult. Which of the following is the main reason for poor weldability of the cast iron? Low thermal conductivity, high carbon content, high ductility, low melting point. Answer will be high carbon content. High carbon content lead to formation of the cementite, that is white iron, which hardens and brittles in HZ. During the welding of the cast iron, the formation of the white iron in HZ undesirable because it increases the ductility, increases the toughness, it is hard and brittle, and it reduces the hardness. Answer will be it is the hard and brittle. White iron contains the cementite, makes it extremely hard and prone to cracking. Which type of the cast iron has relatively better weldability? White cast iron, grey cast iron, chilled cast iron, alloyed cast iron. Answer will be grey cast iron. The graphitic flakes in the gas cast iron provide the stress relief, improves the machinability, and slightly better weldability. So preheating in the cast iron welding is primarily used to increase the cooling rate, reduce the thermal gradients, increase the hardness, forms the martensite. Answer will be preheating to reduce the thermal gradient. So preheating reduces the thermal stresses, prevents the cracking, and minimize the white iron formation. Which filler metal is commonly used for the welding cast iron? Copper, nickel base electrode, aluminum, titanium. Answer will be nickel base electrodes. Okay, nickel electrodes provides the ductile weld metal, reduces the cracking, and accommodate carbon. Rapid cooling during the cast iron welds leads to graphitization, formation of the ferrite, formation of the white iron, increased ductility. Answer will be formation of the white iron. Faster cooling surfaces the graphite formation that results in the carbon from cementite and white iron. Which welding technique is preferred to minimize cracking in cast iron? High heat input welding, cold welding technique, rapid quenching, and continuous welding. Answer will be cold welding technique. So cold welding, low heat input, intermediate welding, and reduces the thermal stresses and prevents the cracking. Which of the following microstructure is most desirable in welding cast iron? Answer will be option A martensite, option B cementite, option C graphite plus ferrite, option D barite. Answer graphite plus ferrite. Graphite plus ferrite are soft, ductile, and crack resistance. Which of the factor increases the cracking tendency in the cast iron welds? Slow cooling, preheating, high thermal gradient, nickel filler. Answer will be high thermal gradients. High thermal gradients means high thermal stresses, cracking in the brittle cast iron. So some of the key points: high carbon content means poor weldability. If we do the rapid cooling of the cast iron during welding, it will form the white iron formation. Preheat treatment, we can reduce the stresses. Nickel filler to improve the ductility, and thermal gradient causes the cracking. Higher thermal gradient results in high crack formation. So next is the welding of the non-ferrous materials. So one is the aluminum. Aluminum alloy has the following characteristics like lightweight, less dense, ductility, no magnetic, and good conductivity, even better than the copper, and forms the high strength alloys with other metals. Fusion range generally 520 degrees to 650 degrees centigrade, and high resistance to corrosion, and intensely used in the used due to attractive physical, mechanical, and chemical properties. So when coming to the welding and welding of aluminum and its alloys, the thin film oxidation present on the surface, this is the removed chemically and mechanically before welding. Oxidation film forms rapidly during the welding. The thin film may contain the moisture, may react during the fusion welding, and liberates the hydrogen to form the porosity. So because of the good conduction of the heat dissipation is very fast. Okay. The thin film oxidation present on the the aluminum has the high coefficient of linear expansion that may leads to the distortion, buckling, and if proper care is not taken. Prone to cracking because of the low strength at the solid is, heat treatable alloy shows the greater tendency to crack. Aluminum does not show any color change on heating. It is difficult to judge when metal begins to melt and proper welding temperature has reached. Indicates Indicators are melting of the dry flux, blasting of the metal surfaces. Coming to the next class of alloys, that is copper and copper alloys are excellent corrosion resistance, electrical and thermal conductive, and formable. High strength and corrosion resistance desired for the marine applications because of good wear resistance. high hardness and corrosion resistance. It is used for the surface of surfacing of the metals. Can be soldered and brazed or welded for the copper. So welding characteristics of copper and its alloys are high thermal conductivity necessitate high heat input into the parent metal. Preheating of the parts may be necessary. So greater thermal expansion of the coefficient may induce the residual stresses. So advisable to go for the slow welding speed or covering the weld joint with the insulating material. Tendency to absorb oxygen to avoid oxidation problem, suitable flux or inert gas is necessary. High thermal conductivity necessitates high heat input into the parent material. The preheating of the pots may be necessary. The greater thermal expansion of the coefficients may induce the residual stresses. So advisable to go for the slow welding speed and cover the weld joint with the insulating material. Tendency to absorb oxygen to avoid the oxidation problem. Suitable flux inert gas is necessary. So some of the welding process we can use for the copper is that tungsten inert gas welding, metal inert gas welding, brazing, and soldering. So magnesium final another kind of alloy is the magnesium. Magnesium the high strength to weight ratio, good fracture strength, high dimensional stability in service, good damping capacity, high thermal conductivity, and good electrical conductivity. Okay, most of the magnesium alloys are readily weldable. Weldability of the magnesium alloy by mostly affected by oxidation, high thermal conductivity and thermal expansion, susceptibility to hot cracking, hot shortness, and grain growth and aging. The stress corrosion for alloying with more than 1.5 percentage of the aluminum, the surface preparation is important. Okay. Next, which process we can use? Tungsten inert gas welding, metal inert gas welding, resistance welding, gas welding, brazing, pressure and forge welding, and electron beam welding. Okay, this is all about the non ferrous materials. Okay. So, which of the non-ferrous metal is most difficult to weld due to hit high thermal conductivity in the oxidation layer? So, answer will be option A copper, option B aluminum, option C magnesium, option D nickel. A correct answer will be aluminum. So, aluminum has the high thermal conductivity that will result in the rapid heat loss and stable oxide Al2O3 with high melting point and difficult to fuse. So generally prefer welding process is the TIG welding with the AC current. So that during the reverse polarity case, the oxidation cleaning layer cleaning will be takes place that will result in good welding. Which property of the copper makes welding difficult? Low melting point, high electrical resistance, high thermal conductivity, low density. Answer will be high thermal conductivity. So copper dissipates the heat quickly, requires high heat input, makes welding pool control difficult. The oxidation layer on the aluminum has a melting point lower than the aluminum, same as the aluminum, much higher than the aluminum, 0 degrees. So it is the much higher than the aluminum. So Al2O3 melts at the 2500 degrees centigrade, while aluminum melts at the 660 degrees centigrade. So provide the proper fusion unless removed. Okay, which process is most suitable for the welding of the aluminum? SMAW, submerged shielded metal arc welding, TIG welding with AC current, oxy fuel welding, and resistance welding. Correct answer will be TIG welding with the AC current. So AC current breaks the oxidation layer and cleaning action takes place, provide the stable arc for the aluminum welding. Which non-ferrous metal is the highest susceptibility to porosity due to the hydrogen absorption? Answer will be copper, aluminum, nickel, zinc. Which one? It is the aluminum. So molten aluminum dissolves the hydrogen during solidification, gas rejection, porosity formation. So which alloy system prone to hard cracking due to the wide solidification range? Pure metals, eutectic alloys, alloys with the wide freezing range, and single phase alloys. So answer will be C. Alloys with the wide freezing range. Wide freezing range extends the moist zone and weak grain boundaries that results in the hot cracking. Magnesium alloys are difficult to weld mainly because of low melting point, high density, high oxidation tendency, low thermal expansion. Answer will be high oxidation tendency. Magnesium forms oxidation layer rapidly, which interferes with the welding. Nickel based alloys generally exhibits it is which defect most common in the welding of copper alloys. Hydrogen cracking, porosity, laminar tearing, preheat cracking. Answer will be porosity. Gases dissolved in the molten copper leads to porosity during the solidification. Which factor improves the weldability of non-ferrous metals? Presence of oxidation layer, controlled atmosphere, inert gas shield, high cool rate, increased impurities. Answer will be controlled atmosphere or providing the inert environment. So shielding gas like argon, helium provides the oxidation formation, improves the weld quality, essential for the non-ferrous metals. So some of the key points are aluminum. What is the problem we face? Oxidation layer and porosity. What is the solution? ACT current and cleaning. Copper, high thermal conductivity. How we can avoid it? High heat input or providing the insulating seal, insulating blanket. Magnesium, oxidation is the major problem. So how we can avoid it? Providing the shielding gas. Nickel alloys, generally good control process. Alloys with wide freezing range, hot cracking, compositional control. Okay, that's it for today.